Hello friends, let's start with our discussion on phase diagram to continue with what we left at the last lecture. Now coming to phase diagram, previously we discussed about phase, what do you mean by phase, what do you mean by component, then we discussed about the Gibbs free energy and Gibbs phase rule. Okay, so now with all these concepts, okay, now we will be able to give our attention to phase diagram, okay, where we will be able to use some of these ideas. So if you look at the slide, phase diagram provide graphical information about relationship between equilibrium phases. So one thing you have to keep in mind that all the phase diagram which you see in the book or any other place, these all phase diagrams are equilibrium phase diagrams. That means that all the phase transformations were done under equilibrium condition. That means very slow. Equilibrium is when we want to have a equilibrium transformation, okay, that means we are able to always go back, okay, and the process is always a reversible process, okay, that is from thermodynamics, that is what we understand, okay. So when I say equilibrium, that means I am doing these transformation very slowly and I am allowing all the diffusion of atoms to take place, so that I can get a uniform composition in each phase throughout the throughout their volume, okay. If you remember, when we discussed phase, we said it has to has homogeneous composition, okay. So to achieve that, you have to do all this transformation at very slow rate, okay, and that is why we call them as equilibrium phase diagram. But in reality, whatever transformation we do, whatever processes we do, they are at much faster rate, okay. So these are not can be called as equilibrium conditions, these are non-equilibrium conditions, okay. So though we understand all the phase transformation from the phase diagram, okay, but in practice we don't practice the same way as we have got the phase diagram. So phase diagram are equilibrium phase diagram, but in practice we don't follow the equilibrium conditions, that you have to keep in mind. So basically it gives you a graphical information about relationship between equilibrium phases, equilibrium phase boundary, etc. at particular condition. The variables can be composition, temperature and pressure, okay. Phase diagram for two components, two different chemical species, are called binary phase diagram, okay. So there can be a unary phase diagram where you have only one component. So suppose if you want to draw a phase diagram for water, let us say, then it will be a unary phase diagram, that means only one component. Or if you have two components, which what we are going to discuss in more detail, those are called binary phase diagram. Then there are ternary phase diagram and so on, okay. So we will going to discuss two component systems which are called binary phase diagrams. Then there are some terms which will come later on in the phase diagram, okay. One is liquidus line, okay. So it is equilibrium line separating liquid phase with liquid plus solid phase. So across this boundary, the liquidus line, okay, you have on one side you have liquid phase, on another side you have liquid plus solid phases. Solidus line, similarly equilibrium line separating liquid plus solid phase with the solid phase, okay. So on one side you will have liquid plus solid, another side you have solid phase. Solvus line, equilibrium solubility of solute in a solvent, okay. So one more line is there which gives you the equilibrium solubility of a particular solute in a solvent, okay. As you remember, we said there will be solid solution. So solute can occupy a substitutional position or interstitial position, okay. So there is a solubility limit, okay, for a given temperature and pressure, above which I cannot add solute atom in a particular solvent. The solute will come out of the solvent, okay. As if you take an example of again water and sugar, up to some point I can add keep on adding sugar, I can dissolve it in water, but after a certain point it will not be able to dissolve more sugar than its solubility limit. Okay. So, then I can keep on stirring, but the sugar particles will remain like that. I can add more, or I can dissolve more sugar by increasing the temperature. Okay. So, that means I am altering the condition to increase the solubility, that is possible, but for a given temperature up to a certain extent I can add sugar in water, but after that it will not take it, because it has reached the solubility limit. You can change the solubility limit by changing some variable, for example, one of them is temperature. So, if I increase the temperature, I can dissolve more sugar now. Okay. Again you will later on reach this solubility limit again. So, if you see equilibrium phase diagram, okay, on the slide there are a lot of applications are there, okay, and for what purposes I can use equilibrium phase diagram. So, it can be used to show phases present at different compositions and temperatures under slow cooling equilibrium conditions. As I told you earlier also, that equilibrium means I have to do it at a very slow rate. So, it shows phases present at different composition and temperatures. At different composition and temperature, what phases are going to be there, phase diagram can tell me. It can be used to indicate equilibrium solute solubility of one element compound in another, as I just told you about water and sugar, that it can give me that what is the equilibrium solute solubility of one element in another, of solute in solvent. It can be used to indicate temperature at which an alloy starts to solidify and the range of solidification. It can also give me at what temperature the solidification will start, at what temperature the solidification will be completed. Okay. So, all these temperature ranges will be given and the fixed temperature can be found out. It can be used to indicate the temperature at which different phases start to melt. Obviously, if I can get solidification, I can also get the melting. It can be used to obtain amount and composition of each phase in two phase mixture. Okay, or when you have two phases in equilibrium, I can find out what is the amount of those two phases, what is the composition of each of these phases. Okay. So, I can get all this information. So, we go to the next slide. Now, we will start with a very simple binary phase diagram, which is called isomorphous systems. Okay. The importance of this particular phase diagram or system is that in these systems both the components are completely soluble in each other. Okay. So, they have complete solubility in liquid and solid phases. For example, copper nickel system, one of the system is copper nickel system. Okay. And the phase diagram is given here. I can explain few things on the board. Okay. One thing I want to bring out here. If you remember in the previous lecture, we discussed about the time temperature curve, okay, and I told you at that time that you can use this time temperature curve to find out the phase diagram. Okay. So, for example, here one time temperature curve is shown, okay, and this is for a particular composition. So, we made one composition, for example, here we have taken 10% B alloy added into A. So, it is A 10% B alloy for which you have got this. Okay. So, this is the liquid phase, at this the phase transformation is started, at this temperature the phase transformation is completed, and then you have the temperature profile in the solid phase. So, from one particular composition, by measuring the temperature of the alloy as we are cooling down, okay, I can find out that at what temperature the phase transformation is started, at what temperature the phase transformation is completed. Now, that information I can use here. So, I can take a 10% alloy here, okay, and these two temperature, if I plot it here, it will give me 2 points for this phase boundaries. Okay, and that is how you can find out for different composition, and you start getting all the points. If you join them, you get the phase boundary. Okay. So, this is a isomorphous phase diagram. Okay. So, I will just use it to explain few things. Okay. So, this is composition is increasing. At this point I have 100% A. So, usually we say A, B and so on. You can replace that by particular elements. So, when if you are talking about copper nickel system, I will say it is 100% copper here, 0% copper here, but 100% nickel here and so on. So, not talking about a specific system, let us say we are talking about any alloy which has A element and B element. At this point it is 100% A, at this point it is 100% B. So, it is percentage B composition is increasing in this direction. Okay. So, as I told you that from that time temperature profile, suppose I take a composition A 10% B, one composition I selected, and then I noted down the temperature as a function of time. Okay, suppose this was the cooling in the liquid phase, then the transformation started, and then the cooling in the solid phase. Okay. So, I got these two temperatures here, okay, for 10% B. So, suppose I take an alloy here of 10% B, let us say this one. Okay. So, I have got these two temperatures T1 and T2. So, these are the two temperatures here, T1 and T2. Okay. So, I got for this particular composition I got these 2 points. Okay. So, similar experiment you will do for other composition. Let us say I take 20% B, then I take 30% B. At all, for all these I will get from the time temperature profile temperatures, and if I start plotting and then I join them, okay, I can get the complete phase diagram between these two systems. Okay. So, this is how you get the phase diagram, one of the method, okay, not the only method, one of the method to get the phase diagram. Now, once I have got this phase diagram, okay, I can see that there are other information which I can take out from it. Let us remove some of this from here. So, this is my 100% B, okay. This is my liquid phase, this is my solid phase, okay. And in between all, whenever there is a phase transformation, in between always there is going to be two phase system, okay. So, here I will have liquid plus solid in equilibrium. So, two phase coexist in equilibrium in between two single phase region, okay. Now, this is 100% A means pure A, or let us say if you talk about copper nickel, if it is pure 100% copper. So, you can see that at 100% copper I will get the melting point of that particular component. So, this is the melting point of A. Similarly, this is 100% B. So, this will be your melting point of B. From here it goes from solid phase to liquid, because these are pure ends, okay. There is not going to be any two phase region at these points, okay. For any other composition there is going to be two phase mixture. So, liquid plus solid and solid, okay. Now, as I told you, we discussed few terms, okay. You have two boundaries here, okay. So, we said that a boundary between a liquid phase and liquid plus solid phase will be called as liquidus line. Boundary between liquid plus solid and the solid will be called as solidus line. So, we get from this we get at for a given composition, okay. I have to fix a composition for a given composition here, at what temperature the solidification will start at what temperature the solidification will complete, and then the solid phase will start below that particular temperature. Okay. So, few things we can see, we can get from this particular phase diagram. Okay. Now, I will give you some, there are couple of more terms which will be helpful for us to get information from the phase diagram. If you remember the first slide, we said that there is lot of information which you can get from the phase diagram. Okay. So, there are two things which we can use to get the information about the phases present in the phase diagram. Okay. One of the idea or one of the term which we use is called tie line. Okay. What is tie line? If I want to find out the composition of phases in two phase region, I have to draw a tie line. Tie line is nothing but a isotherm. Isotherm is at a constant temperature. If I am taking something, then it is a isothermal condition. Then I have to identify the points where the tie line is cutting the phase boundaries, draw vertical line from these points cutting the composition axis. Okay. So, now my interest is, suppose I have taken an alloy, let us say I say that this is my A 20% B alloy. So, in this alloy 80% is A, 20% is B, it can be weight percent, it can be atomic percent, I am not going into that detail right now. Okay. It can be weight percent for simplicity, that I am took A 80%, let us say I want to make a 1 kg alloy. Okay. So, I have taken let us say if I have to make 1000 gram alloy, okay, I will take 800 grams of A, 200 grams of B, okay, melt them together, then I will get 1000 grams of alloy. Okay. So, that is what I have done. I made an alloy, I took it into the molten condition, found out the temperatures at which the transformation starts and transformation is complete. Okay. And from there you have got this information. Okay. So, this is the overall composition of the alloy. Now, I want to know that what is the composition of the liquid phase and what is the composition of the solid phase at a particular temperature. So, at this particular temperature my transformation starts, at this particular temperature it is over. Okay. Suppose at this particular temperature, okay, I want to know that what is the composition of the liquid phase, what is the composition of the solid phase. Okay. So, what I will do? I will draw a tie line. Okay. A tie line is an isotherm, that means it has to be drawn at a constant temperature. This is my temperature, this is my composition. So, I will draw a tie line, okay, which will be parallel to the composition axis. Isotherm will be parallel to the composition axis. Okay. And now, this wherever it is cutting these two phase boundaries, okay, that will give me the composition of each of these phase. Okay. So, if I want to know what is the composition of liquid phase, what is the composition of solid phase, this will be the composition of solid phase, and this will be the composition of liquid. Okay. So, you can see that overall composition is A 20% B, the composition of solid is less than that. So, maybe it is around, you can say it is A 10% B for example, and composition of liquid will be let us say it will be A 70% B. Okay. So, in between during the solidification there will be lot of separation of B atoms between solid and liquid phases. Okay. So, initially the liquid is what we say solute rich, the solid is solute poor, okay, or deficient. Okay. As you keep on going to lower and lower temperatures, we can keep drawing tie lines like this. Okay. At the temperature where the transformation is completed, there if it is done in a very slow rate in equilibrium condition, the last when the total solid is forming, okay, and there is no liquid left, then the last total solid will be solidifying with this overall composition with which we started. So, in the liquid phase it started from here, then the separation of solute atoms started between solid and liquid, okay, it keeps on going, and then the last, when the solidification is completed, the whole solid is having the same composition as the overall composition. But this is only possible when you are doing it very slowly. Okay. As you can see, understand that the first initial solids which are formed had very low percentage of B, okay, and as we keep coming, okay, the solid which is forming has high concentration of B. So, we have to give enough time for this solute atom, the B atoms, to diffuse within the solid and have the homogeneous, overall homogeneous composition, okay, so that when my solidification is completed, the full solid volume will have only one composition. Okay. So, this is what do we mean by equilibrium solidification, or the solidification which is following the equilibrium phase diagram. Okay. So, tie line I can use to find out the composition at intermediate levels. Okay. So, to find out the composition of solid phase here, wherever the tie line is cutting the solidus line, that will give me the composition of solid. Wherever the tie line is cutting the liquidus line, that will give me the composition of liquid. Then there is another very important concept called lever rule. Okay. So, maybe I will remove few things from here. I will just remove this. Sorry. Okay. Now, again I can take a tie line here, okay, as we just discussed, and suppose I am taking a composition like this. This is my 100% A, this is my 100% B, this is how my composition of B is increasing, okay, and this is temperature, and this is a tie line. Now, one thing we have already seen, that I can get the composition of each phase. Okay. So, this is liquid, liquid plus solid and solid. So, this will give me the composition of solid, and this will give me the composition of liquid. Okay. I can say Cl, and I can say Cs, and this is the overall composition C naught. Okay. Now, there is a concept in mechanical systems also, which is called lever. Okay. So, when you have a lever, you have if you have a fulcrum on which this lever is balanced, okay, I can balance it like this. Okay. This can be called as lever, there is a fulcrum there. Okay. So, I am trying to balance. Okay. So, basically when I am trying to balance, if I take a larger arm length here, then I have to put more force here. You can see that it is going down there. So, I have to put a force here, okay, larger force here, and that force will be in proportion to what is the length of the arm on both the side of the fulcrum. Okay. So, when the arm length is more here, I have to put more force here. Okay. So, there is, to have a balance in this lever arm, okay, if I have a larger length here, my force F1 will be more. So, if L2 is greater than L1, to keep it in equilibrium, okay, or in balance, okay, I have to have a larger force F1 compared to force F2. So, in this particular diagram which is given on the slide, L2 is more than L1. Okay. So, my F1 has to be more than F2, okay, and the proportion in which it has to be more will be in the same proportion in which the L2 is more than L1. Okay. So, their proportion has to be same. So, in phase diagram, okay, tie line can act as a lever arm with fulcrum at the overall composition. So, where you have overall composition, there can be a fulcrum. You can see that it looks like a lever arm. Fulcrum can be at the overall composition. The force at each end correspond to amount of phase at that end. So, what is the fraction of this phase and what is the fraction of this phase will depend, will can have an equivalence with the force at these end. So, if my arm length is more here, I will have more force here, that means I must have higher fraction of this phase. I have a smaller arm length here, so I will have lesser force here, so this phase will have a smaller fraction. Okay. With the help of lever rule, one can calculate proportion of phases in two phase region of phase diagram. So, from the phase diagram, okay, in the first slide we said we can find out what are the different phases present in the phase diagram, that now I can tell you, you have liquid phase, liquid plus solid, solid. I said that we can find out the composition of each of the phase. So, if I have taken a certain composition in liquid phase, it has composition of C naught. In liquid plus solid region, it has solid has composition of Cs, liquid has composition of Cl. Now, I also want to find out what is the fraction of each phase, for which I am going to use lever rule. Okay. So, if I want to know what is the fraction of the solid phase in this two phase mixture, okay, what I will do is I will take the arm length here, which is which will be given by Cl minus C naught, that will give me the arm length here, and that I will divide by the total lever arm, which will be Cl minus Cs, and this will give me the, suppose this whole phase diagram is in weight fraction, what will be the weight fraction of solid phase. Okay. If I want to know weight fraction of the liquid phase, okay, then we have to take this arm length. So, this will be now C naught minus Cs divided by total length Cl minus Cs, okay, total length. This will give me the weight fraction of liquid phase. Okay. So, I can now find out what will be the fraction of each of the phase also. Okay. Or if I have the weight fraction of solid phase, okay, if I subtract this from 1 or 100%, then I will get the weight fraction of liquid phase. So, if you calculate one also, you can easily calculate the other by subtracting out of 100%, or you can say if it is in fraction, then out of 1 minus weight fraction of the solid phase will give you the weight fraction of the liquid phase. Okay. So, I can use this analogy of mechanical lever to find out the fraction of each of these phase, and then we will use this when we will do the assignments, we will use this to find out all this information from the phase diagram. Okay. With that, I will say thank you, and in the next lecture we will try to see other types of phase diagram. This was a isomorphous phase diagram where the two component has complete solubility, but there are other phase diagram or systems where the solubility is not complete, then what type of phase diagram you get. Okay. Thank you.